Ventilation Network. So I'm Kath Noakes. I'm just going to give a very brief introduction to this afternoon, and then I'm going to hand over to Tim Sharp, who's going to chair this afternoon's meeting because I have to disappear off shortly. But just to give you a sort of quick introduction to the beginning, I guess just before we start, to just put a few rules in place. Please can you stay on mute until we get to any point where we ask questions, and use the chat function to ask the questions when we get to the panel discussion, or to indicate that you want to ask a question. Yeah, so just to give a kind of introduction to today, first of all, I think many of you know about Future Urban Ventilation Network already, but for those of you who don't, we are a UKRI funded network that's under this SPF Clean Air programme. We're one of 6 networks that focuses on indoor-outdoor exchange and basically thinking about indoor air quality. Helen has just very helpfully put the link in the chat to our website, and we focus very heavily on all aspects around ventilation, so thinking right through from the technical aspects of how we understand the connections between outdoor air in a city and indoor air in a building, and to what people are exposed to, through to how you design and manage good ventilation, and then through to what it means for policy and regulation. So we've set this webinar up to celebrate the very first ever World Ventilation Day, which we're really pleased to have started today. It is, you know, the first time this has been done. We're really happy that we've got world buy-in for this. So it started off as a small conversation between a small number of us, and a bit of discussion on social media, and snowballed into the Future Urban Ventilation Network working with BISA, who have been absolute stars behind it in terms of the marketing and the website and the social media side of things, and with SIBSI and with IMECE, and as a starting point to kind of spin this up into something that would work. And then we have gained support from all around the world, from organisations who lead on ventilation, including ASHRAE and RIVA, as well as people like EASYAC and the British Occupational Hygiene Society. So we're really pleased, and if any of you are on social media today, and look at the hashtag on World Ventilate Day, there's a huge number of organisations who are sharing things around ventilation today. So the purpose of today is really about celebrating ventilation. We've got 4 fantastic speakers working in different areas, different career stages, worked on different types of ventilation projects, and are just going to share some of their experiences of working on those, and then there'll be a panel discussion afterwards. So without further ado, I'm going to hand over to Tim, who will be able to chair this, introduce the speakers, and take you through this afternoon.
Thanks, Kath, and sorry you've had such difficult transport issues this afternoon, but I'm very happy to share. So good afternoon, everybody. I'm just going to, without further ado, I'm going to hand over to our first speaker, who is Andy Acred from Foster+Partners, who's going to be talking about sharing novel ventilation strategies which have been used in Foster+Partner projects. Andy, are you okay just to share your screen?
Sure. Let me just see if I can get this to work.
Okay, so just feel free to add questions into the chat, and I'll try and pick some of those up at the end and we have a bit of time for discussion. Okay, sure. I can see that. You
can see that? Fantastic.
Yeah, to you.
Okay, great.
So next speaker is Filipa Adzic. So high resolution CO2 monitoring at live theatre events to assess ventilation and mitigate airborne transmission of SARS and COVID. Are you able to share, Filipa?
Okay, hoping you can see that now.
Yes, I can see that.
We can see it. It's on. You're not quite on. That's it. Okay, ready to go.
Okay.
Fantastic.
Brilliant. Okay, so hello everyone. My name is Filipa, and today I will be talking about some high-resolution CO2 monitoring we did in few theatres. So just to give a brief overview, I am currently working as a research associate on the AIRBODS project. Some of you might have heard about it. It stands for Airborne Infection Reduction through Building Operation and Design for SARS-CoV-2. Please do go on a website, check it out, see more details about all the work packages we're involved in. The work I will be talking about today has already been published in Building an Environment COVID-19 special issue. And although I'm giving this presentation today, this work is a result of a huge team effort, and it was led by Leora Malky-Epstein as a work package leader and Malcolm Cook as a main project investigator. So to start with, we can all remember the closure of mass gathering events as it proved to be very crucial in pandemic mitigation from very early on. In the first 12 weeks, over 15,000 theatre shows were cancelled, causing a huge loss in box office revenues. In Spain and Germany, governments initiated research programs that will investigate the spread of SARS-CoV-2 in mass gathering events, and the UK government followed this, setting up events research program, which is the largest program of its sort to its date. The aim of this program was to provide evidence which will allow the government to assess and mitigate the risk of mass gathering events and spreading of the pandemic. And the events research program was organized in 3 phases, and it ran between April and July 2021. A range of venues over different occupancy events were monitored, and because of the project's impact, it meant that the data collection, analysis and reporting had to happen very, very quickly, with usually just a couple of days for collection and analysis of data. So you can imagine this was quite an intense time. Amongst other research methods, high-resolution CO2 monitoring was deployed to assess ventilation provision in different spaces within these large venues. And as part of the ERP, we also monitored different events, including sports venues, nightclubs. But today I will focus this talk on monitoring 7 different theatre auditoria over 82 live events that were operating within or shortly after the events research program. I'm very happy that I can give this talk to you today because personally I'm a big fan of the theatre. So why did we do the CO2 monitoring? As it's widely known, ventilating indoor spaces dilutes and removes airborne viruses. We've all heard this story before. So CO2 and virus concentrations in air have no direct correlation, but CO2 can definitely be used as a proxy for evaluating ventilation. So just wanted to briefly go through this table that was developed for the events research program by our group. And it was used to mainly classify the spaces we monitored quickly. So this table specifically was developed based on existing British standards, SAGE and CIBSE guides. And to just give you some perspective, medium air quality in this table is something that is a normal expectation level for an office. And spaces that were classified as F or G for prolonged periods of time are identified as priority for improvement. So just a brief overview of the venues and events we monitored. It's quite a nice mix of spaces. We had some of the venues such as Piccadilly, Lyceum and Grange theatres are more than 100 years old. And others such as Crucible and the Playhouse in Leeds were built in the last 50 years. and the O2 Arena and the ACC Conference Centre in Liverpool were built in the last 20. So in total, 7 venues were monitored over 82 events with varying occupancies, and they are also different period buildings. They all had mechanical ventilation in the auditoria, and some were supplying seats beneath some were supplying air beneath the seats and extracting at ceilings, and others were supplying at high levels and extracting below the seats. So it's really a mix of mechanical ventilation strategies. And just a brief overview of how we monitored the CO2, you can see the little sensors we used. They logged CO2 temperature and relative humidity every 2 minutes. The majority of the sensors were installed at the back of or under the seats, within the breathing zone of occupants, and away from ventilation components such as inlets. Sensors were transmitting data through gateways into an online dashboard, which could be monitored by the research team during the events, but we also logged the data for detailed analysis after the events. So when I say high resolution monitoring, what exactly do I mean? Mostly, I mean installing a large number of sensors within one space, such an auditorium, and separating the space in multiple monitoring zones. You can see how zones might be defined in a single space in the top image here. And each zone would have 2 sensors, and it would consist of a few rows grouped together. Apart from monitoring one space at high resolution, multiple spaces within these venues were also monitored based on their use. So it's important to note that in theatres, obviously not all spaces within that venue are for performance watching. There are also, for example, bars which are used completely differently. There's arrival areas, there's dwelling areas. So it's important to just keep that in mind, that it's not just the auditoria. Why is it beneficial to do high resolution monitoring, you may ask? So I'll just show you some results to highlight this. The graph in this slide shows CO2 over an event in Lyceum Theatre, which was 94% occupied. And as the auditorium is highly occupied, we can assume that the seating was uniform. So not people weren't grouped in just one section. What this graph shows us is a drop in CO2 during the interval as some spectators left the space for a short time. And we can also see that the spectators seated in balcony and circle sections were exposed to 34% higher CO2 concentrations than those seated in stall sections. And high resolution monitoring and installing several sensors at different auditoria sections made it possible for us to see that the air is not well mixed in this auditorium. And if the CO2 was only measured at stalls level, the entire auditorium would be classified as medium air quality band D. But it's obviously not the case everywhere. So the ventilation is not effective here because of insufficient outdoor air supply and insufficient mixing of air as well. Here we have a 90% occupancy event in the Grange Opera. And this is an interesting case because this event includes a 100-minute interval at which the spectators leave the auditorium and grab food, drinks for 100 minutes. So you can see the drop in CO2 during that time. The Grange Opera presents with even higher difference in sensors measuring CO2 at store levels and balcony and circle sections. And it's almost 60%, 57% higher. The ventilation system in this case supplies outdoor air under the seats in the stalls area, and the air is extracted at the ceiling level. So by design, the CO2 levels at the top are higher with increasing vertical height. As well as in the Lyceum Theatre, high resolution monitoring leads to detection of poor air mixing in this case. Okay, so I just wanted to talk about the effect of airing occupancy as well. This is the Crucible Theatre. During World Snooker Championships, we monitored a range of occupancies here from 8 to 88% full capacity. And average and maximum CO2 values were calculated from all the sensors in the auditorium at each event, and both average and maximum CO2 are rising with occupancy. This indicates that the ventilation system is not demand driven. And the highest occupancy event is in the bottom graph here, and we can see that depending on where the spectators are seated, they are exposed to different air quality, which also shows poor mixing of air. So just to go through the overall air quality in all the theatre zones that we monitored, I feel that I've only shown you some scenarios that could have better ventilation, better air supply, better mixing of air. But I wanted to make it clear that the average air quality for all auditoria zones monitored was mostly in A or B class for 70% of the time, actually. And the maximum CO2 classifications varied, which is an indicator of poor air mixing and CO2 spikes. Maximum CO2 measured in each zone over all events showed that 41% of all zones had medium air quality, and 37% were in bands E or F. Just to make some conclusions, high resolution CO2 monitoring allowed us to identify if the air in theatre auditoria is well mixed and distributed. This is very important, as effective ventilation doesn't only depend on ventilation rates, but also the appropriate distribution of outdoor air to all areas. In the theatre study that we published, we made a recommendation that event intervals can be used to reduce CO2 concentrations and overall exposure to exhaled breath. But it's important to bear in mind that crowding issues of other spaces within the venue can occur. Overall, most zones within the auditoria had average of A or B class air quality, which is good. CO2 monitoring can be used to inform quickly about areas that need improvement and in which scenarios improvements are necessary. This was highlighted during the events research program when we had to deliver results in seemingly impossible deadlines. And finally, the high resolution monitoring does not have to be permanent. It can be only temporary, and this can provide very valuable answers in a short time period. Thank you for your attention, and yeah.
Great. Thank you very much. Thank you, Filipa, and thank you for putting up with that rather difficult and unpleasant situation. So very, very smoothly picked up then. I think what we'll do is we'll just press on with the speakers, if that's okay, because we've obviously lost a little bit of time here. If people can stay on at the end for questions, then we'll do that. So yeah, with no further ado then, Ben Roberts from University of Loughborough. If you're going to come next, speaking about the AIRBODS project and ventilation strategies in Ghanaian hospitals.
Yes.
Ben, you've got to go. Indeed. Over to you.
Thanks very much, Tim. Okay, hello everyone. Yeah, my name's Ben Roberts. I'm a doctoral prize fellow at Loughborough University, and I'll be talking about some of the recent ventilation projects I've been doing, just to give you a taste, in both temperate and tropical climates. So the first project I'll be talking about is the one that follows on from what Filipa has been talking about, that was done as part of the AIRBODS project. And this was the first ever nightclub event to open after the pandemic. We were lucky enough to be in there monitoring the air quality. And we've got a paper that's been accepted to be published very soon on this. So the nightclub event was held over 2 nights, 30th of April and 1st of May in 2021. And you can see here they packed 3,000 people into a large warehouse in Liverpool. And it really was a huge space. We had 33 CO2 sensors placed around in cages, which we thought would be a good idea because 3,000 young people having been locked away for a year might be a bit rowdy. But as it happened, they're all very well behaved and we recovered all of our sensors. So it was a huge space with huge ventilation openings. It was 160 meters long with 7 by 7 meter ventilation openings. So we thought, great, there's 6 of these huge doors, only on one side, so there was no ability to cross ventilate. But there was certainly the ability to have sufficient ventilation through these openings. We had 2 main parts of the warehouse. One end was a dance floor and the other end was a bar area. Now, the dance floor area, that had, first of all, you remember these huge doors, they pulled the shutters down halfway and then put plastic butcher screens across. And this was all about trying to reduce air moving in and out of the, noise moving in and out of the venue, but it actually had the effect of stopping air from moving in and out of the venue. The bar area, which was down at the far end, this actually had the full doors open throughout the event. So here's just an example of butcher screens in case you don't know quite what I'm talking about. So yeah, so the event kicked off, 3,000 people packed into this warehouse watching a variety of DJ sets. And here's some of the results. So the bar area, which was at the far end with the 3 big open doors, that's this yellow line along the bottom. And throughout the event on the first day, actually the CO2 levels remained quite low, which indicates there was a reasonably low risk of exposure to exhaled breath, which may or may not be contaminated with virus-laden aerosols. However, close to the front of the stage, which was where people were densely packed and those ventilation openings were blocked, CO2s were much higher, particularly on the far side, furthest away from the door. CO2 levels remained quite high through the majority of the event, but the event from around 5:30 in the evening all the way up to the event closure at 11 o'clock at night, CO2 levels at least above 1,600 parts per million, which indicates a high level of occupancy relative to the ventilation that was available. So just to explain graphically, the worst place to stand if you were wanting to get exposed to other people's exhaled breath was at the front of the crowd. The best place to be was right at the back in the bar area, having a drink, popping in and out of the big open doors. Something interesting happened on the second night. We saw at certain half-hour marks, a sudden drop in CO2 concentration. And what we realized was this was happening when a DJ was finishing their set. People were suddenly rushing out of the venue through these openings. And in doing so, they were opening up the butcher's doors, increasing the ventilation rate, and also reducing the emission of CO2 because there was fewer people in there. So what this kind of tells us is that had these doors have been open, potentially ventilation would have been sufficient for the number of people, but it was because the doors were closed that caused the problems. So we had very high CO2 far from the door, but intermittently higher CO2 close to the door openings. And we were very pleased that some of the events were covered in the newspapers. It's not often that ventilation research makes the front pages. We've got 2 papers. So one's a conference paper, which has already been published, which you're very welcome to go and have a look at. Another paper will be coming out very soon. There's also a blog on the AIRBODS website, which you can go and have a look at. The second part of my presentation, for a bit of variety, is talking about some of the work I've been doing in naturally ventilated and air-conditioned hospitals in the tropics. And I recently published a conference paper on this, which you're also welcome to go and have a look at if you want to read more information. So climate change is driving increasingly high temperatures, and particularly in the tropics, which are already very hot places to be. And so because of that, hospital buildings are increasingly being retrofitted with air conditioning units, which are recirculating air conditioning units which provide cooling without introducing fresh air ventilation. And here's an example you can see on one of the more modern hospitals in Ghana. We have these sliding windows, which obviously block half the potential ventilation opening when they're opened. These could be twice the size if louvered windows were used. And so because of that, air conditionings needed to be installed to provide thermal comfort. So the aim of my project here is to use ventilation to provide low or zero energy cooling whilst diluting airborne viruses and preventing mosquito-borne diseases. So that's not just a case of opening up and allowing maximum amounts of ventilation, because that would potentially let mosquitoes in. So I've got 4 hospitals in my study. I'm just going to present some of the results from 2 of the hospitals today. In some of the wards, we have mechanical ventilation, particularly in the modern hospitals. The image on the right, this is a neonatal intensive care unit. So we have very vulnerable occupants, small babies, which are they have such little fat content in their body, they're not able to maintain their own internal temperature. So we have to provide a thermally comfortable environment for them here. But in most of the other wards, they are naturally ventilated with either louver windows in the older hospitals or sliding windows in the new hospitals. You can see on the right-hand side, I've circled in red, that's one of the recirculating air conditioning systems that's been installed. The wards can be very crowded, so not only have we got patients in there, there's usually visitors and also a large number of nurses, doctors and trainees. So we installed CO2 sensors using a very similar methodology that was used on the AIRBODS project, so CO2 sensors installed around the various hospital wards. And then to classify the air quality, just using this very basic classification of 950 parts per million. So we want CO2 to be below that value. And I'll show you some results now from the rainy season in Ghana, which 28 degrees, I found it very, very hot and uncomfortable, but I was being told by everyone who was living there, this is the cool season, we feel cold. So here's the CO2 concentrations in the 2 hospitals. And whilst most places, most wards had very low CO2, the ones with the yellow circles around, these are the wards with recirculating air conditioning. And I think it's no coincidence that the ones with the recirculating air conditioning had the highest CO2 concentrations. Just to look at some of the carbon dioxide profiles now, in this ward, we were told there was children who were under 6 months with their parents. And the parents were telling the nurses at nighttime, my children are too cold, so please close the windows. And you can see this, the windows were closed towards the end of the profile, the CO2 concentration builds up overnight, and then around 6 o'clock in the morning, the windows were open and the CO2 concentration drops. So here, clearly there was sufficient ventilation through the windows, but because the windows weren't being used effectively, the air quality was potentially poor. In the emergency ward, the ward was constructed with other wards around it on 3 sides, and the only window openings to the outside being blocked by 2 beds at the back of the ward. So here, to provide thermal comfort, windows weren't used, but the recirculating air conditioning system was used. So here, we had potentially good thermal comfort provided by the recirculating air conditioning system, but very poor air quality with CO2 concentrations, in some cases over 3,000 parts per million. So whilst air quality was satisfactory in most wards, it was the recirculating air conditioned wards where the air quality was poor, and it was the thermal comfort and concerns about mosquitoes, which I didn't mention, which are the main drivers of window opening, not concerns about indoor air quality. And you can read my latest conference paper on this here. So thank you very much for listening.
Brilliant. Thank you very much. Great stuff. Okay, so we'll just go on to our last speaker, Leora Melchior-Epstein from University College London, who's going to be talking a little bit about the cave facility.
Yes, thank you. I just need to be able to, here we go. Can you let me know if you see this properly?
Yep, that's good.
Okay.
Okay, far away.
Okay, so this talk is a bit different to the other 2. I was very pleased to have Ben and Filipa's talks first, because it's really the work that we've all been doing together as a group that has been very exciting, very rewarding, and a very, very busy time for us in the past few years with the pandemic. One of the things that really came out of all of this work was that there was a really clear identified need to have a space that could be better controlled, where we could do experiments on ventilation and not be kind of at the mercy of field studies, because what Ben and Filipa didn't really give a sense of, because they're so professional, is just how challenging these field studies are, how difficult they are, and how rare it is that we would be given access to such venues in the first place to be able to measure ventilation there and report on it. So what we have started doing at UCL over the past few years, there is a very large-scale facility called Pearl. It's a research lab led by Professor Nick Tyler from the Department of Civil Engineering at UCL, where we're based as well. This is now located in Dagenham, so in East London, where you can still get the space to run facilities like this. And because of what has been happening with the pandemic, it was decided to build a separate thermally and ventilatedly controlled lab just next to it. And that lab is the Controlled Active Ventilation Environment Lab, or CAVE in short. So the field studies, you've seen a few field studies now in the previous talks. Obtaining permissions for monitoring and for sharing data can be quite challenging. Sometimes people just don't really want to participate, or they might want to participate mainly if they think the results will be very good, which is not entirely helpful. The projects also, between getting into local risk assessments and having to transport equipment on site and working safely around their usual activities that are already going on, mainly, especially when you're talking about live events that have a lot of people around, that was quite challenging. What is quite nice about a lab as well that can be done, besides the fact that you can start building long-term collaborations between academia and industry and research agencies and the professional bodies that actually look at design of ventilation, we can really on a physical level just create controlled conditions. We can maintain those conditions for a while. We can use them to validate models because we can take measurements at quite a lot of detail. We can then generalize the results to other settings so that they might be more useful for learning lessons from. And of course we can test, for example, changes. So if we see that there's an issue with some sort of ventilation system, for one thing, we can test it at a whole range of different temperatures and scenarios. For another, we can then start tweaking things and seeing what the result is in a realistic environment. Obviously, you wouldn't be able to do this at a venue up to a point. So again, this is the architect's rendition of CAVE, just to give you a sense of the size of the lab and the fact that it can house a double-decker bus. There's also specifically an opening to allow vehicles and buses to go in, because besides working on events, we've also worked on public transport, and that is also an arena where understanding ventilation systems is quite important. So this is the kind of conceptually what the lab looks like. On the right side, you'll see there are the kind of control rooms, and there's a basic biolab, so that we could also experiment a bit with distributing plant viruses, or even just collecting samples and preparing them for further analysis if we have humans in the space and we just want to see where their bacteria is going. The main issue here, of course, is that it's very, very substantial in terms of plant space. So the entire roof is taken up with plant equipment. And the main lab, which you see on the left, I showed you before a picture of what it would look like if a bus came in. This is a picture of what it would look like if we build a house inside. So the size of the space, it's 220 square meters, and it's almost 10 meters tall. So we could construct potentially almost at realistic scale a 3-story house, or a theater with several levels, or again, the double-decker bus, all kinds of constructions that allow us to actually test ventilation scenarios at the real scale, so that they're not modeled in a lab on a small scale, because the modeling doesn't translate 100%. And this is just kind of conceptually, you can see the plant equipment. So what happens in this lab is that there will be a separate ventilation and cooling and heating system for the environment itself, and that can be control down to -5 degrees. It can be controlled up to about 40. So just to replicate kind of typical environmental conditions in Northern Europe, and 40 degrees is no longer is such an imaginary scenario even for the UK. And there's a separate ventilation system also controlled centrally that will service the space that is being simulated. So either the mock-up of the house or the mock-up or the actual bus or vehicle that would be in the space. And by controlling the two systems separately, we can actually see things like how does the air exchange between them. So looking at kind of traditional research capabilities, there's a lot of work that can be done at a very, very small scale. There are environmental chambers. There are a few around the world. This is just an example from Purdue, and there's an air pollution test chamber from University of Surrey. And what we're trying to do is to scale all of this really up to be able to capture the sort of problems that we see in real life. So it's transport where you have really a lot of people. There are indoor spaces like the ones that Filipa has talked about, kind of theaters. There's interactions indoors in very large buildings where you have several stories or mezzanines and you want to see what happens vertically with the air. There's exchange of pollution between the indoor and the outdoor. So for example, in street canyons. And then CAVE is kind of designed to look at all of these kind of things. So its capabilities would be the transport vehicles, the public spaces, and that means restaurants, theaters, school, healthcare, any type of space that is being used by many people. And we've designed CAVE to allow us also to introduce people into the space. So potentially we could have possibly up to 100 participants who actually come in, and then we can see how the environment affects them. You know, are they comfortable? Are they happy? What are they doing? How are they performing cognitively if we're simulating a school? And at the same time, also see what the people do to the environment. So the lab is really kind of designed to address major challenges in the built environment that we're living in at the moment. So we're looking at population growth, at urbanization, and at climate change. And the problems we have in our cities now, it's overcrowding, it's traffic, which really leads to air pollution, transmission of infectious diseases. Everyone is now fully aware of that problem. And of course, trying to balance those with minimizing energy consumption and carbon emissions, when in fact the solutions are almost exactly at odds with each other. So although the building design guidelines are great and they're perfectly appropriate and there are lots of technical solutions to improve things, we don't actually know what the quality of ventilation is in the UK. And again, finding out that knowledge is a humongous task, and yet it was very, very important when we tried to make plans for infection control and wanted to know what is the state of the nation, how is ventilation working in practice around the UK. So with CAVE, we'll be able to kind of classify the built environment, test the human interactions with them, and characterize them and measure them to the nth degree, and then create these kind of realistic scenarios that are hopefully representative of what happens out in the world, so that we would be able to then estimate at least what could be happening everywhere else. So we can look at just specific kind of project ideas, testing solutions to reduce the risk of poor air quality, so kind of retrofitting, testing ventilation technologies and low energy that are low energy and climate efficient, quantify the actual trade-offs. So if you try to address one target, what actually happens, what are the unintended consequences of this? And how can you quantify the energy consumption when you're heating up or when you're cooling down a space? And also to understand, when we have people in there, how do we actually improve their experience? So their experience of architecture is something that is very important for architects, and to understand their health, their well-being, their comfort. So this is the situation at the moment with CAVE. It's under construction. There are pictures from March, from June, and from September. It hasn't changed very much since September on the outside, but the inside is becoming finished now, and we're hoping to be operational in February. So watch the space. Very excited about the whole thing.
Brilliant. Thank you very much indeed. Thank you. Really interesting stuff. I'm sure. When's it due to be finished?
So February 23. Well, fingers crossed. Of considering the state of the world, you can't really predict anything these days, but it seems like it will be.
It's a construction project after all as well. There are. Indeed. Okay, great. Listen, we've got a little bit of time left for kind of questions and discussion. So I'm just looking for people to kind of put their hands up. And I'll just either put your hands up and I'll grab you, or stick a question in the chat alternatively. Just while we're waiting, I've got a couple of questions quickly for the speakers. Filipa, in the events program, am I correct in remembering that those theatres were being used to their full capacity? There was no social distancing at that point, and were people wearing masks as well?
So it really depends on the phase of the events research program. Some of the theatres were tested in a range of capacities. The ones I presented today surely did. I picked the ones that were almost at full capacity to show you. Others weren't. Others were at much lower capacity. So please, for more detail, the paper that's been published is open access. So feel free to just type it in Google Scholar and check it out.
Yeah, no, it's interesting. No, I think that's interesting. Kind of testing things in a sense at their worst is important. I mean, I think what was interesting about certainly those talks was the ability for this kind of monitoring to identify problems, and not everything is a problem. So the ability to kind of focus attention on those bits which are perhaps kind of worst off, I think is very kind of interesting. I've also got a question for Andy. Andy, in your building, presumably that's a fairly big building, right, with very high occupancy loads. So presumably most of your loads are cooling loads. Is that correct?
Yeah, that's true. We've got, it's quite when it is full, because we're mostly back in the office now, but there are still days when people work from home, so we've got varying occupancy now. But yes, when it's full, lots of heat gains. We've got lots of high powered computers in here as well, lots of people. So yeah, mostly cooling, yeah, during the summer.
Okay, so my question to you, a slightly more general question, is in smaller buildings which may want to have natural ventilation, it's this difficult decision we make about good levels of ventilation or maintenance of thermal comfort and energy consumption. Is natural ventilation possible in smaller buildings in which we are trying to conserve energy and heat loss?
Yeah, I would say so. So are you saying that the issue would be with the sort of punching holes in the building fabric, sort of compromising the thermal performance of the building?
Well, no, I suppose it's, certainly with domestic, for example, or small building, it's NVHR is becoming hard to avoid, certainly in terms of kind of compliance. Is that a fair statement, do you think?
Well, I think it's about controlling when you do the ventilation. I think that vent is still, it's simple. It should be considered. You need to have big enough openings, and they need to seal when you close them. But by giving that control to people, I don't know. I think you have a lot of benefits because you end up with adaptive thermal comfort. People feel comfortable in a wider range of temperatures. But yes, like you say, maybe NVHR is, I mean, that's passive house, I guess, has pushed that forward a bit. But I would say that natural ventilation should stay as one of the options that we have, because it doesn't require any power at all. So if there are going to be, for example, rolling power cuts, maybe you can still use that then. Yeah, no,
I mean, it's an interesting potential problem. You know, again, think about domestic and NVHR and people on power cards, things of that nature. Yeah, okay. No, thanks for that. I suppose a slightly more general question then is where you think we're going with this in terms of you know, clearly a lot of building change has been driven by the energy agenda, quite rightly so. So things we've done in terms of thermal performance, air tightness, all that kind of stuff. What do you think is going to have to change? And the general sort of perceived wisdom is that sort of ventilation requirements have lagged behind a little bit. What do you think are going to be the sort of the significant changes coming up, do you think, in terms of designing for, you know, for better comfort, for better air quality?
Is that to all of us?
It kind of is, yes. Yeah, it's sort of to everybody, but yeah, feel free to go ahead on it.
If I can, I'll take the first bite then. So, and just to note as well, we have a few questions in the chat now. I think many of us are really hoping that indoor air quality will go much higher up the agenda, because there were already very good reasons to improve indoor air quality even before the pandemic. It's not just about infectious disease, and it was about the unintended consequences of all this work on energy, that sometimes it comes at the expense of ventilation, and people just forget that we do actually need fresh air as well. But there's a real risk, I mean, now with the cost of energy and the crisis and climate change crisis and everything, that the idea gets lost. So it's very exciting to have this World Ventilate Day and to keep it very high up the agenda as much as we can.
Okay, so yes, so we have got some questions in the in the chat. So Darren, do you want to just? Yeah, so you say you've got what you say you've got a question for Andy. Maybe do you want us to just say what that question is?
Can you hear me?
Yeah, we can hear you fine. Yeah.
Oh, hi there. Yeah, it's just we quite often segregate the thinking behind indoor air quality and ventilation, and then the other aspects, obviously energy, heat loss in winter, and overheating. So quite a lot of the submarines that we saw in the cities are full height glazing, and obviously overheating and cooling requirements become a much greater concern, and we need to think of everything at the same time. So my question relates to full height glazing, what the latest thinking is, how that leads to overheating, and flow rates that you need to get through your building to keep that under control, and then obviously whether that outweighs our requirements on indoor air quality and associated infection resilience.
Yeah, thanks for that, Darren. I think I would say the issue with all of this full height glazing, because obviously it's not necessarily the best idea in terms of thermal performance of the buildings, and we have gone a little bit brute force with the way that we, you know, condition our buildings when the whole, you know, the external facade is all glass. I think that's in some ways a style thing. You know, very aesthetically driven designs, people like all glass. But I'm hoping that we are starting to move away from that. We do, certainly in my team here, we'll look at like early stage design, we'll look at facades. So we do projects all around the world, and we'll very quickly try to run through different scenarios of different glazing ratios, for example, and try to select the one that's best for that particular climate, that particular location, the sun path, etc. Ultimately, it is still driven by the architect and the client. So sometimes you might still end up with your glass box. In terms of the knock-on effects to HVAC design, yes, it would make sense to have lower glazing ratios, better self-shading, more external shading, because then you can downsize your HVAC plant. But I'm not sure if I could put any sort of numbers on that, because I tend to work more in the concept design phase. But I hope that's
yeah, I think well, the quick question, I think, is does it stop the ability for us to naturally ventilate more buildings when we've got full height glazing?
Yeah, I would say it probably does, because you can still have double facades, but it would be better to, first of all, shade, keep the sun away, and then open up the building for natural ventilation. So yes, I would agree that, generally fully glazed buildings are not great for natural ventilation.
Okay, thank you.
Great, thank you. Yes, and of course, what that also tells us, we've got a retrofit problem as well with all those existing ones. Question from James. So this is about CO2. If I understand your question correctly, James, it's the difference in dispersal between CO2 and aerosol. Is that, have I got that right? Do you want to just correct me if I haven't?
Yeah, that's right. Yeah, I thought about it when you were talking about the theatre experiments with the CO2 vertical profile, whether that sort of thing would be expected the same in an aerosolized, such as a virus is. I believe a virus is in aerosol when it's exhaled. So how close is proxy of using CO2 to what's actually happening? And has much work been done on that?
I can say that one of the work packages of AIRBODS project is focusing on looking into aerosols, I believe, but currently I'm not sure how directly it would relate. I wouldn't want to say anything that's not true at the moment, but I think it's very fascinating. I think, that probably might even be the next step of this sort of a research to connect the two.
I mean, I'm aware that there was some work going on through the Health and Safety Executive Protect project, which was looking at aerosol distribution in spaces. I mean, what strikes me from your thing, Filipa, is that clearly that movement is what, well, I say it's obvious. Is it obviously being driven by heat, by warm air rising? That's what's driving that distribution.
Yes, and just the positioning of where the extracts and the inlets were placed as well. But I presented maybe some, I didn't present a theatre where the air was well mixed. So these were just the cases where we found that in most other places this didn't happen.
Okay, great. All right, thank you. And so a question from Jill. Did any of the theatre spaces make improvements? And if so, what did they do?
So in theatres, obviously it'd be quite difficult to replace a whole ventilation system right now, but we did communicate the results in some spaces such as O2 Arena. The building managers did want to know what the air quality was like, so they can increase the operation of the ventilation system. But we did have spaces in the ERP, in the events research program, that during the events we would see the air quality is not, the CO2 is above 2,000, and we would tell the event operators and building managers, and they would put in a mitigating measure, or put an extractor in, disperse the crowd. It happened only in a few places, but yeah, we do have experience of event managers and building managers acting on it. Laura, please add if you can remember anything else.
Yeah, I think that there was definitely one case where it was just there was a space that was poorly ventilated, and it just turned out that the ventilation system was set to recirculate only, and in other places we found sometimes that the system needed to be maintained. So just having the information is a good start, but refurbishing an entire theatre or building and changing their ventilation strategy wholesale is actually really beyond. It's not something that is easy to fund, especially in today's climate. So
it's not. Ben, I was going to ask the same question of you of the hospitals. Did they do anything?
Well, at the moment, I've done a very short period of monitoring, but certainly as the project continues, I'll be making interventions. But just to go back to the theatre paper, one of the key findings was that intervals are really important things. So if you can't afford to make big upgrades to the ventilation system, you just keep people outside of the actual auditorium for a longer period, allow the ventilation to do its thing, and then bring people back in. Hospitals don't have you can't ask people to leave the ward if they're bedbound. So there it will be more dependent on the ventilation, either the ventilation system or use of the windows.
I mean, that thing about who does what, I think is quite interesting. So yeah, that I was going to ask, you know, the interval thing is in a sense an operational change you could make. So slightly contentious question. Do you think if people who use the theatres were aware of the CO2, should people be aware of CO2 levels in spaces in which they might occupy?
I believe so, especially if you might be concerned or consider vulnerable. That is something I'm working on currently, and hoping to publish with the rest of the team is what exposure are you going through an entire event based on how you behave and where you're sitting. So I do think people should know and make their own decisions. But I also think people should be educated on you know what's considered, maybe consider risky or not risky.
I think this
is that's interesting, isn't it? About yes, what is bad, because those levels, they were high, but they were not disastrously high. If you
no, that's actually an important point, that the overall air quality found throughout the events research program was actually very, very good, and there were kind of 10% of the spaces had identifiable issues some of the time. And even those issues that we're talking about, normally CO2 levels up to about 1500. So not the kind that led to the super spreading events that were very famous during the pandemic. So people need to be concerned where they're vulnerable, or where, you know, this kind of thing like, oh, I'm about to go on holiday, I don't want to get COVID just before. But at the same time, once the population is vaccinated, people don't need to be worried about CO2 all the time either. So we want to balance the hypochondria with kind of a alertness and education, but without going overboard, because the situation is not that bad.
You know, I think this is interesting about, you know, what is bad. I mean, I think the other bit about this is this concept. So someone mentioned earlier, we are quite good at, in a sense, as humans, we can detect thermal comfort and we will react to that. I think Ben, no, in fact, Andy, you were saying, you know, people, if they're hot, they'll open the windows, and, you know, we know that stuff. But because as humans, we can't detect ventilation or air quality in the same way, the fact that CO2 becomes a proxy at least gives us a visual indicator of something which might start to change people's behaviours in some kind of way. You know, I was aware of a couple of things. So there was a thing, I think in Belgium, there is a requirement for cafes and stuff to have CO2 sensors and display that. And I've seen some stuff about some places in Japan. You know, there's an app that people can get to sort of, you know, see what it's like before they choose to go there. Yeah, interesting.
I think there's can I just make a quick comment on that?
Yeah, please do.
Because I think part of where we're getting to now is there's sort of a maturity in the Internet of Things market. So there are a lot more consumer sensors available for monitoring that can talk to everything. I mean, this is what we're trying to do here with our iPads that show people information, and it's becoming easier to do that now. So then I guess there's a case of the question is, how do you present that information to people? Because as Leora was saying, you know, we need to balance up, you know, do you want to tell people to be worried, or do you just want to present them with the information and then also sort of educate them as to what that information means? Because I think if you give people too much, it might be overwhelming and people might overreact, or, you know, I think that's a big discussion to be had.
Yeah, no, interesting. And that so the question from Hilda, I think is relevant to that. So, you know, we know that 600 to 800, you know, 80 per second per person is ideal, but it should perfect be the enemy of good in this respect. You know, what should we be aiming for?
So on that, actually, we did do a lot of work on this, on the AIRBODS project, and also in collaboration with other projects like Track and Viral, and Kath Noakes has done a lot of work on this, that basically the risks are only substantial when ventilation is very, very poor, and the risks are substantial if you're sitting next to someone who is infected. So then you're at risk of droplets transmission and aerosol transmission, and even surface transmission. But that whole idea that you could sit in a room and there would be a super spreading event, that doesn't happen at 1,000 ppm. From experience, there were a very small number of very, very publicized events. But if it had been happening all the time, we would have seen that at the events research program. We would have seen it all over the place every single day. And that isn't actually what happened. So prioritizing the very poor spaces is the best strategy, rather than kind of getting very worked up about whether it's 1,200 ppm or 1,000 ppm or 800. And yes, for offices, it's been determined a long time ago. 800 is great. People feel very comfortable. They're very productive. They're happy. They're healthy. They don't have headaches and nausea. But again, it's not about every single space at 1,400 ppm now being, requiring evacuation or anything. So,
and of course, in some buildings, particularly naturally ventilated buildings achieving 600 to 800, there's going to be a thermal and an energy penalty to that, of achieving that. Again, we sort of saw some feedback. A lot of schools in September 2021, opening windows and getting very uncomfortable and not great either. And so just after a question about indoor air quality in schools. Yeah. Anybody want to comment on that? I mean, I know that schools were, have been included. There have been several projects which have done that. I can say that there was work done in Scotland which was doing CO2 monitoring of schools. Again, if it was the same sort of finding, is that very few of the rooms were so significantly bad, to warrant sort of action. And that action tended to be a relatively simple thing. It was literally sort of ungluing the windows and things like that. Okay, we are at the end of our allotted time. And there's a link there to the school's work as well, which may be useful. Thank you to all our speakers this afternoon. Really interesting and insightful stuff. Obviously, this is an ongoing thing. There's lots of stuff happening. I think it's telling us a lot about buildings that we didn't really know beforehand, and I think that's a really good thing.